Hey guys, how are you all doing? I'm hoping that you all are doing fine. You all must be healthy and fine. Excellent guys. This is Sagar Darvi, your chemistry teacher, and I welcome you to this batch of excellence. Well guys, it's been quite a few days that we have been meeting frequently to learn the syllabus of organic chemistry. And I'm sure that you all are aware that in our course we just not study the syllabus of your boards, but we are also learning this organic chemistry with respect to your competitive examination preparation such as JEE and NEET. So guys, in our today's class, we are going to start with a brand new chapter that is nothing but amines. So this is Sagar Darvi, your chemistry teacher, and I welcome you to this brand new chapter that is amines. So guys, are you all ready to go ahead? Excellent. So before we start, as always, we'll first see our today's learning objective. So let's see precisely what are we going to learn. So since it's the beginning of a new chapter, we'll be first getting introduced to several types of amines. We'll study the structure of amines. Followed by, we'll also talk about nomenclature of three different types of amine like primary, secondary and tertiary amine. Once that is done, we'll be entering into some simple methods of preparation of amine that will include preparation by Hofmann's ammonolysis, or sometimes this is also called as alkylation of ammonia. We'll then talk about preparation of amines, precisely speaking primary amines by Gabriel thialamide synthesis. A very commonly asked question comes from this reaction. We'll then talk about reductive amination of carbonyl compounds. So you'll see how aldehydes and ketone upon reaction with ammonia or derivatives of ammonia followed by reduction gives you corresponding amines. And then guys, we'll be talking about four very important reactions, or you can call them as rearrangement. The most important one as far as this chapter and the entire organic chemistry is concerned is about Hofmann's bromamide degradation. So from this chapter, yes, this is a very important reaction. You can just scroll back to all previous year question and you'll certainly find many a times this question have been asked, okay? And of course, I'm talking about various examination, not the same question you'll see repeated in JEE as such. So we'll be learning Hofmann's bromamide degradation. Just like last time we saw Arndt-Istad reaction, which was a process for the upgradation in the number of carbon atom, that is chain lengthening. Here we'll see the degradation of the carbon chain. Then we'll be talking about Curtius rearrangement followed by Schmidt reaction. Hofmann-Curtius, well, there is one reaction missing in between. We'll be talking about Lawson rearrangement as well. Then Schmidt reaction followed by a reduction of nitriles and oximes resulting in the formation of amines. And then we'll also be talking about by the reduction of nitro compound that helps us to form the corresponding amines. So guys, let's get started straight away with the introduction and the structure of amines. Well everyone, so as to begin with amines, let us consider ammonia as our parent compounds, and we are going to assume hypothetically that we are going to do some changes in the structure of amines by a simple process of substitution reactions. Alright, so let's say we have ammonia as our starting compound. So ammonia contains center atom nitrogen with 3 hydrogen atom attached to it along with one lone pair. And now we are assuming that in this ammonia we are going to do some small changes in terms of substitution reactions. So let's say one hydrogen atom of ammonia is substituted by one alkyl group. If that happens, NH3 will now exist as RNH2. Well, you will see here now nitrogen is directly connected to only one carbon atom because there is only one alkyl group attached here. So such nitrogen will be considered as 1 degree or primary nitrogen atoms. Hence, an amine would be referred as primary amine. Alright, so if you see in ammonia, if you replace just one H with one alkyl group or maybe an aryl group, you call such amine as a primary amine. Similarly, let's say that we are replacing two hydrogen atoms with two alkyl groups, which may be identical or may be different as well. Then the product obtained will appear as RNHR. Since we can see here that nitrogen atom is connected to two carbon atoms directly, such nitrogen will be considered as secondary carbon or 2-degree carbon atom. So such amine will be referred as secondary amine. And if we substitute all the three hydrogen atoms of ammonia with, let's say, three alkyl, which could be again identical or maybe different, then the corresponding product obtained can be represented as R3N with nitrogen carrying lone pair. So no hydrogen seen on this nitrogen atom. That clearly indicates all three H's have been substituted by three alkyl groups. Because nitrogen in this case is connected to three other carbon atoms directly, we call such nitrogen as tertiary nitrogen or 3-degree amine. So this is our 3-degree amine. So guys, based on how many alkyl groups directly connected to nitrogen atom, we have classified these amines as primary, secondary and tertiary, and all of them seems to be obtained from ammonia by replacing required number of hydrogen atoms with the equivalent number of alkyl groups. That clearly indicates that all the amines are the alkyl derivatives of ammonia obtained by replacing one or more hydrogen atoms with the equivalent number of alkyl groups. And that's how we define amines. So amines are nitrogen containing organic compounds which are derivative of ammonia obtained by replacing one or more hydrogen atoms with the equivalent number of alkyl group, which could be same or could be different. Alright guys, well, now when you talk about such amines, there is sometimes a point of confusion. For example, let's say if I talk about, I'm comparing now some examples of amine with alcohol, let's say, okay. So let's say if we have ethyl alcohol, and if someone asks us what's the degree of alcohol, we say here OH is connected to primary carbon atom, hence such alcohol will be called as primary alcohols. Similarly, now let's say we have got examples such as ethylamine. And if someone asks us what's the degree of amine, again nitrogen is directly connected to only one carbon atom, right? So the degree of nitrogen is primary, so I'm calling it as primary amine. Understand the difference here. When we are defining degrees of alcohol, we are looking at the degree of carbon atom to which OH is connected. So you're calling it as primary alcohol. When you're looking at degree of amines, you're looking at the degree of nitrogen, as in the nitrogen of amine is directly connected to how many carbon, and that is defining the degree of nitrogen, hence the degree of amine. So this is a primary amine. Just to distinguish this, let's say if I have got 2-butanol, and if someone asks us to find out the degree of alcohol, you will say OH is connected to secondary carbon, so this is secondary alcohol. Now if I just change function of OH to NH2, just change the function of OH to NH2, structurally it will look like this. Now we say this is secondary butyl alcohol, we say this is secondary butyl amine, but what is its degree? Well, here we are not going to see nitrogen is connected to which degree carbon. Nitrogen is connected to secondary carbon, that is for sure, which is this carbon. But to find out the degree of amine, we look for the degree of nitrogen. Tell me, nitrogen is connected to how many carbon? Nitrogen is still connected to only one carbon. So still this is a primary amine. So everyone understand the difference. This alcohol which we have got is secondary alcohol. So the degree of alcohol is decided on the basis of degree of carbon atom to which function group is connected. The degree of amine is decided on the basis of degree of nitrogen atom. Nitrogen is still connected to one carbon, so it's a primary amine only. So secondary butyl alcohol is secondary alcohol, whereas secondary butyl amine is a primary amine. In simple words, what you can do is look for that nitrogen atom. How many H's do you see? 2 H's, which means Considering this as a derivative of ammonia, how many H's seems to be replaced by an alkyl group? Only one, because ammonia is NH3, has got 3 H's. I still can see there are 2 H's, meaning one seems to be replaced. Because one is replaced, we'll call it as primary amine. The moment you see NH2, it is always going to be primary amine. So sometimes this could be point of confusion. I want you to have a clarity on that. Alright guys, so that was introduction of amines. Now let's talk about the structure of amines. Well, so if you look at all these amines, you will find it contains nitrogen atom with at least one alkyl. Of course, we are talking about amines, and the remaining valency are satisfied by hydrogen. Let's talk about the tertiary amines. In case of tertiary amines, you will see nitrogen is connected to 3 carbon atom and 1 lone pair. So considering that these alkyl groups are aliphatic alkyl group where lone pair are not in conjugation with any of the atom, so it appears like this nitrogen has 3 bond pair. Well, structurally, if I talk now, NR3 rather, here the central atom nitrogen, let's assume it to be A, has 3 bond pair, so I'm writing it as B3, and 1 lone pair, so I'm writing it as L1. AB3L1 indicates that the total electron pair are 4, 3 in terms of bond pair, 1 in terms of lone pair. So total electron pair 4, meaning according to steric number, what we learn in chemical bonding, let's call it 4. Steric number is basically the one which gives you information about total number of electron pair on the central atom, which could be sigma bond pair and a lone pair. Sometimes there could be only sigma bond pair. So here in this molecule, we have got 3 bond pair plus 1 lone pair, that is total 4. So when the total is 4, the expected geometry of molecule is tetrahedral. Which means when you talk about central atom nitrogen, the 4 electron pair will be oriented at the 4 corner of tetrahedral geometry. For example, if I have to put those electron pair at the 4 corner of tetrahedral geometry, we will end up drawing them like this. So that's going to be nitrogen. Now when you talk about tetrahedral geometry, we represent like this. We first draw 3 bonds, and then this is, let's say, 4th. However, we know that all are not bond pair. There is 1 lone pair. So this I am now making as a lone pair. Okay, and let's call this as alkyl group R, R, and R. Well, precisely if we have to represent the structure in 3 dimensions, we can also represent it this way. Let's say I'm removing this bond pair. One of the bond pair I'm representing on a solid line. Hold on, everyone. So there has to be 1 bond which is going behind the plane of paper, which we are representing on, let's say, dashed line, or you can say hatch bond. Right guys? So you'll see here in this molecule, 1 bond of alkyl group is in the plane of paper. Another one is coming outside the plane of paper on the solid wedge or solid line. And there's 1 more which is going behind the plane of paper, dashed line, or you can say hatch line as well. Well, in such case, the 4 electron pairs, 3 bond pair and 1 lone pair, are oriented at the 4 corner of regular tetrahedron. But because all are not the bond pair, if I talk about the shape of molecule, lone pair will never be included in the shape of molecule. So you have got central atom N right here, and 3 bond pair which appears like this. Right everyone? Now just imagine if we try to attach these corners starting with N. The molecule somewhat is looking like this. So if you see the base of this geometry has got 3 atoms. Which 3 atoms? This 1, 2, 3. And the overall molecule looks like as if it's a pyramid. So pyramid on the base of 3 atom, and hence such geometry is said to be trigonal pyramidal. So we say amines are found to be having a shape of trigonal pyramidal. So guys, understand one thing. In case of amines, since it belongs to type of AB3L, steric number 4, we expect that those total electron pair, meaning 3 bond pair and 1 lone pair in this case, to be oriented at the 4 corner of tetrahedral geometry. That is expected geometry. But the moment there comes 1 lone pair, that is never included in the shape. So the shape of molecule, ignoring this lone pair, appears like it's a trigonal pyramidal. So we say all amines are found to be having trigonal pyramidal shape. Further, if we talk about the hybridized state of nitrogen atom, like I said, assuming this lone pair are not in conjugation with any of the alkyl group, so this nitrogen has 3 bond pair plus 1 lone pair. That is steric number was 4. Steric number 4 meaning its hybridized state is sp3. So the nitrogen atom is found to be in sp3 hybridized state. Further, what is going to be the bond angle? Well, in general, when we say the geometry is tetrahedral, so let's say whatever group is present here, let's say R and R, bond angle is expected to be 109 degree 28 minutes precisely, like it is observed in case of methane. However, now not to forget, we have got 1 lone pair present here and 3 bond pair. So according to VSEPR, lone pair interaction is found to be the maximum repulsive interaction. Then lone pair bond pair, and the least repulsive interaction is found to be in case of bond pair, right? So if we compare the same over here, you will see there are 3 bond pair interaction, 1, 2, and between these 2 bonds. But there are 3 lone pair bond pair interaction as well. Now because lone pair and bond pair interaction or repulsive interaction is more, this lone pair will push all these bonds little downward. If they come little downward, the angle between the 2 bonds will decrease. Hence the ideal bond angle is not found to be 109 degree 28 minutes, but it is lesser than that. And considering this tree as an alkyl group, let's say as a methyl group, this bond angle experimentally is found to be very close to 108 degree. And that's why, considering the all value of alkyl as methyl, you will say the shape of such molecule is trigonal pyramidal with C and C bond angle as 108 degree, where the nitrogen atom exists in sp3 hybridized state. So guys, this is the structure of amines. Well, one important information. Now let us say if we have this 3 alkyl group as a different alkyl group, so we can represent the nitrogen in this way. Let's call this is R1, R2, and R3, carrying 1 lone pair. If you look at such nitrogen atom, all the 4 valencies are satisfied by 4 different groups. 3 of them are alkyl group and 1 of that is lone pair, which is also considered to be satisfied by the different valency, let's say, right? So when you talk about lone pair and bond pair, here everyone, since all the 4 valencies are satisfied by different groups altogether, in fact lone pair is also considered as one of the hypothetical valency. So such nitrogen atom is found to be a chiral nitrogen atom or asymmetric nitrogen atom. And having said earlier in stereochemistry, if in a molecule there is only one asymmetric atom, that molecule is always optically active. And yes, this molecule with 3 different alkyl group and lone pair is found to be optically active. However, the problem is such nitrogen which is carrying 3 bond pair and 1 lone pair, which is optically active, hence expected to be existing in the 2 enantiomeric form, that is dextro and levo. But those 2 form dextro and levo of such amine does not exist in reality because the separation of such 2 amines become difficult. Now why separation of dextro and levo form of such amine becomes difficult is answered by a term that is called as nitrogen inversion. So guys, let us understand something called as nitrogen inversion. Well, nitrogen inversion says such tertiary nitrogen atom is found to be in an equilibrium mixture of these two. So that's R1, R2, and R3. So this first amine, the first amine changes or undergoes inversion into the second amine. As soon as this is formed, this rapidly undergoes interconversion of first amine. That's why although these two are the chiral molecule and the mirror image of each other, meaning these two are enantiomeric form of each other. However, these enantiomers cannot be isolated from each other because the inversion between these two is very rapid. So these two forms will undergo a rapid inversion, and because of rapid inversion, separation of such two molecules is not possible. Further, it is believed that at this point of time in this two enantiomeric form, the nitrogen atoms are in sp3 hybridized state. But this inversion, the flipping of molecule, takes place by an intermediate form of such amine where nitrogen exists in sp2 hybridized state. So just trying to give you visualization, imagine that this lone pair which is present as of now in sp3 hybridized orbital, if all these three alkyl group comes vertically in the same plane and the lone pair goes in pure p orbital. So pure p orbital will not be part of hybridized orbital. So only three hybridized orbital left, which are representing these three bonds. So 3 meaning sp2. So this sp3 molecule will be first converted to sp2, which we have not shown here, followed by into another sp3 types of molecules. So because these two optically active form of amine being rapidly interconverting into each other, we cannot isolate them. Because we cannot isolate them, we say although theoretically such amines should be optically active, it is in general optically inactive because separation of two molecules is difficult. But imagine if the fourth valency of nitrogen, which is as of now satisfied by the lone pair, if it is forming a coordinate bond with the fourth alkyl group, that is R4. So there will be 4 bond pair. In case of 4 bond pair, inversion won't be possible. For inversion to take place, there has to be presence of lone pair in an hybridized orbital. So NR4 plus, that kind of amine with all 4 alkyl group being different, will exist in enantiomeric form, and certainly that can be separated as well. So guys, that was some information about classification and the types of amine, followed by how do we precisely find out degree of amine based on degree of nitrogen, and that's the structure of amine. Alright everyone, now proceeding further with a simple part. I'm sure you all are aware how to do the naming of amines. So firstly, when you talk about amines, as we have seen, primary amines are represented as RNH2. That's primary amine. Secondary amines represented as R, NHR, identical or different alkyl groups, whereas tertiary amines are represented as R, N, R and lone pair. Now when you talk about the naming system of these amines, primary amines are named as alkanamine. Of course, we have to be very precise the number of carbon atom where the amine group is present. When it comes to secondary amine, they are named as N-alkyl, alkanamine. While deciding that which alkyl group has to be considered as alkyl and which alkyl has to be considered as a parent alkane, of course we look for the number of carbon atom. Any alkyl which has more number of carbon will be considered as a parent, as alkanamine, and the remaining alkyl will be considered as a substituent present on the nitrogen atom. Whereas tertiary amines are represented as N-alkyl, 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 alkanamine. Now assuming that two of the alkyl groups are identical and the third one is the one which contain more number of carbon atom, then the third one is going to be a parent compound, that is parent chain, and the remaining two alkyl, if they are identical, then another way of writing the name is considering both alkyl together as N, N dialkyl. N, N dialkyl alkanamine. NN dialkyl alkanamine. Now let's take example to understand this system of nomenclature. So guys, let's say if we have got as an example CH3CH2 NH2, the simpler one first. So other than NH2, this is the longest continuous chain of carbon atom that we have got. Once we select the longest continuous chain, we have to make sure that the functional loop is present at the lowest possible carbon. So this is 1 and 2. 2 meaning indicates parent chain eth. Since carbon-carbon single bond in and functional loop is amine, so the E of ethane is being dropped since we cannot write two vowel adjacent to each other. So the name is ethanamine. Ideally speaking, NH2 is present at carbon 1, so we should have written ethan 1 amine. But in case of ethane, wherever you put, that locant is going to be always 1. So when the position of functional loop is always identical, no matter which way you number, then we do not mention that locant as such. So this is called ethanamine. One more example, let's say the secondary butylamine example that we had taken earlier. Let's take that again. Let's say this is the structure given. We'll first identify that carbon of the longest chain which is directly connected to functional loop. So functional loop is connected to this carbon. So this carbon should be a part of longest chain. Once you select longest continuous chain, then the numbering is to be done to the carbon of longest chain so as to receive lowest possible number at the carbon carrying functional loop. So I must number from left to right. So 4 indicates word root is but. Carbon-carbon single bond. So in we are dropping E because E is a vowel and the suffix name for amine is again amine, which is having a first alphabet which is again a vowel. So the E is being dropped. Now this amine is present at locant 2, so you have to mention butane 2-amine, or you can also write it as 2-butanamine. Alright, see why I mentioned 2 here, because had this NH2 been at the terminal carbon, that would have been butane 1-amine. So there are 2 different positions possible. So you'll have to specify that where that amine is present. Coming to the secondary amine, well, let's say we have molecule like this. Now clearly we have got 2 different alkyl group. Right everyone, one is methyl, other is ethyl. Now the alkyl which contains more number of carbon will become your parent. So that's going to be the parent. So select the longest continuous chain. This will be considered as a substituent present on N. So just like you said an alkyl, you'll call it as N-methyl. In the longest chain, I'm doing numbering in such a way that functional loop secondary amine is attached to the lowest possible number. So I've got methyl present at N. So the naming will be N-methyl. Present on a parent chain containing 2 carbon, that is eth, carbon-carbon single bond in amine. So the name of molecule is N-methyl ethanamine. N-methyl ethanamine. Now just to take one more example, let's say now we have got C2H5. NH CH CH2 and CH3. Well, valence is not satisfied here, so let's put one more CH3 here. Okay, now again, this is smaller alkyl, this is the alkyl having more number of carbons, so you'll have to select a longest continuous chain here. So don't directly start from the carbon to which nitrogen is connected. this is going to be your longest continuous chain, indicating functional group secondary amine is present at the second carbon, 1, 2, 3 and 4, and this will be considered as a substituent ethyl present at the nitrogen. So how will you start? Ethyl present at N ethyl, 4 meaning but, carbon carbon single bond meaning ane, and amine present at number 2, so butane 2 amine. So the name of molecule is N-ethyl butane 2-amine or N-ethyl 2-butanamine. Likewise, guys, let's say we have got molecule where 3 alkyl groups present at the nitrogen atom. Now all have been identical, so any one of that will be considered as a parent chain and the remaining 2 will be considered as a substituent. So let's say these 2 are considered as a substituent. This is the parent chain of 1 carbon. So 2 substituents being identical, which are methyl, we'll call it as N, N dimethyl, N dimethyl, and the parent again contain 1 carbon meaning methanamine. Alright. Similarly, imagine if these 2 would have been different. One would have been methyl, other would have been ethyl, and other would have been propyl. Okay, let's take that example just to make you understand the alphabetical order. So C2H5 N CH3 CH2 CH2 and CH3, let's say. Now here, that's a parent chain where functional group nitrogen, that is amine, is present at 1 of propane parent compound. Ethyl and methyl, see alphabetically this is ethyl, this is methyl, are the 2 substituents. And now we are supposed to write down substituent first. So when you have got 2 different substituents, check their alphabetical order. Like this is ethyl, so you will say N-ethyl, followed by N-methyl, N-ethyl, N-methyl, and then prop, carbon carbon single bond, propane amine, but amine is present at number 1, so you'll have to mention propane 1 amine. Propane 1 amine. Alright everyone, so that's how the nomenclature of amines have been done. We have taken 2 examples of each primary, secondary and tertiary amine. So guys, that was all about the basic introduction of amines, how amines are defined, how are they obtained or how they are considered to be obtained. Followed by, we also saw the structures of amine. We learned the concept of nitrogen inversion, in what case we should consider the amine as the optically active compound and in which case we should not. Whenever there is nitrogen inversion, meaning when there is one lone pair present, we will not consider that to be optically active. But for different alkyl group present with the bond pair present there, like NR4 plus, you will consider that as to be optically active amine. And then we saw nomenclature of amines. Now what is left is a methods of preparation. So quickly starting some simple methods of preparation of amine. The first one is by ammonolysis of alkyl halide. This is sometimes also called as by alkylation of ammonia. Well guys, let's try and understand this simple reaction. Look, let's say if we are talking about a general form of reaction, guys hold on. Okay, so let's say we have got ammonia, which we are allowing to react with alkyl halide. Assuming again this alkyl group of alkyl halide to be lesser sterically hindered like methyl, primary or at the most secondary. Now what we have studied in reaction mechanism, halogen being more electron negative acquire delta minus charge and the carbon of alkyl acquire delta plus charge. Such deficient alkyl group will always be attacked by the electron rich nitrogen followed by departure of halogen simultaneously. Assuming this is lesser sterically hindered alkyl group, we get formation of RNH3 plus and X minus, right? RNH3 plus and X minus. Well, I'm writing that X minus here. So basically what we're getting is alkyl aminium halide salt. Alkyl aminium halide salt. Now the molecule which we have got is further subjected to the treatment with the base. So either we have got separate base such as OH or the similar molecule of ammonia which we have got here. Let's say that ammonia, the second equivalent of ammonia, is accepting H plus from here, and that's how we got formation of RNH2 carrying a lone pair. See, once the proton have been extracted by ammonia and to come out as ammonium ion, that is NH4 plus, this is being converted to RNH2, which is nothing but primary amine. Alright, so basically what we have eliminated is NH4 plus X minus. Now if you look at this compound RNH2 which is obtained, now the nitrogen atom is now connected to alkyl group. Here the starting compound was just ammonia having all the three H's only. Now because here there is one alkyl group connected to nitrogen which will show electron donating inductive effect, electron density on nitrogen will increase. That makes such nitrogen even more basic. Lewis base are electron pair donor. Hence such amine which is obtained as a product of alkylation of ammonia. See, in ammonia 1H is substituted by alkyl, so we'll call it as alkylation of ammonia. So such amine being even more basic than ammonia, and if alkyl halide is in excess, then this ammonia will attack at the second molecule of alkyl halide as well. So let us assume I'm continuing the reaction thereon. If we are assuming alkyl halide in excess, so let's note that as well. So what will happen? This will be second equivalent of alkyl halide. Lone pair of nitrogen will attack to give you RNH2 plus R. Of course X minus will leave. And now this will be further undergoing deprotonation with the ammonia which we have got. So this ammonia will carry out abstraction of H. So we'll be getting formation of secondary amine. So now what we have got is R2. Two alkyl group I'm writing together. R2NH, which is nothing but secondary amine. Now two alkyl group present on nitrogen will show even more electron donating inductive effect, which will make nitrogen even more electron rich, hence more basic or more nucleophilic. So this is all set to attack at third equivalent of alkyl halide. So let's say this is alkyl halide, lone pair attacked here, halogen left as X minus, producing R2 N H and R carrying positive charge on it. So there is still one more proton left. So ammonia will now again carry out deprotonation process here, so that this bond pair will go back on N and neutralize this N. So we'll be getting formation of R2NR. R2NR, nothing but a tertiary amine. So if you see this overall process, when ammonia is treated with excess of alkyl halide, we are not just getting primary amine, we are getting mixture of primary, secondary and tertiary amine. Hence this method is not really preferred for the formation of primary amine. However, if we intend to prepare primary amine as a major product, again only obtaining primary amine will be difficult. What we can do is we can take excess amount of ammonia and limited amount of alkyl halide. So that possibility of getting primary amine as a major product will be more. Hence remember, taking ammonia in excess, so we are changing the concentration. Treating that with alkyl halide. Of course, if ammonia is in excess, we'll have to consider this is limited amount. So followed by attack of departure of X minus, we will be getting RnH3 plus ammonia will further carry out deprotonation, and that will result in the formation of RnH2, which is nothing but primary amine, and I would say that this is obtained as a major product. Alright guys, well, another way of looking at this reaction is we can also say that we are breaking the carbon and halogen bond of alkyl halide. So we are carrying out lysis, breaking of carbon halogen bond using ammonia. Hence this is sometimes also referred as ammonolysis of alkyl halide. Hence we call this process as by ammonolysis of alkyl halide, or can also be considered as alkylation of ammonia, because if you see the first way we have represented the molecule, ammonia was our starting compound, all the three H's have been substituted by alkyl, so you can call it as alkylation of ammonia as well. Conclusion: alkylation of ammonia will always result in the formation of mixture of primary, secondary and tertiary amine. However, if we intend to prepare primary amine as the major one, then we'll have to take ammonia in excess and alkyl halide in limited. That will not deny the probability of getting all three amines, but majority of the product is going to be primary amine. That was first method of preparation, guys. The second one is another important called as preparation of amine by Gabriel phthalimide synthesis. Okay, let's try and understand the Gabriel phthalimide synthesis, and then we'll also understand the important features of this reaction, or maybe you can say limitation of the reaction. Well, so to understand Gabriel phthalimide, we'll need to first understand phthalimide. As the name indicating, it's a imide of phthalic acid. So in the previous class we discussed in the carboxylic acid, aromatic dicarboxylic acid, that is phthalic acid. We are preparing its amide. We are preparing its imide. Imide is secondary nitrogen connected to 2 carbonyl carbon. So that's secondary nitrogen. This is phthalimide. This phthalimide is treated with base. So let's say we are treating this with KOH. So this phthalimide is found to be quite basic, hence we are allowing it to react with KOH. So KOH being base will attack at protic H. The bond pair will go back to give you N minus, which is balanced by K plus. So we're going to get a salt of phthalimide, that is potassium salt of phthalimide. So we'll be getting that is N minus and K plus. That is phthalimide, and this is potassium salt of phthalimide. Okay, now this potassium salt of phthalimide is allowed to react with alkyl halide. Now this is an important step, alkyl halide. Now understand one thing, since we are allowing it to react with alkyl halide and electronegativity difference across carbon halogen bond is developing a polarity across the bond, we can see the carbon of alkyl group is electron deficient, hence indicate that it is electrophilic in nature. Electrophilic carbon will be now attacked by the nucleophilic nitrogen atom. When such nucleophilic nitrogen is attacking at the carbon, for such attack of bulky nucleophile group takes place, the value of alkyl group has to be a smaller alkyl group such as methyl or primary or at the most secondary. So the degree of alkyl in the alkyl halide has to be the lesser sterically hindered preferably. So X will leave, so X minus is leaving along with K to give you Kx. So minus Kx, see what we have got. So here N carrying alkyl group with the lone pair intact on it. So we had phthalimide. With base, it gave you salt of phthalimide, which is nucleophilic in nature, hence undergone nucleophilic substitution reaction with lesser sterically hindered alkyl to give you N-alkyl phthalimide. This is N-alkyl phthalimide. Now this N-alkyl phthalimide is further converted to primary amine by two ways. Either you can carry out simple hydrolysis of it. Imagine if you carry out hydrolysis of it. So let's say this bond is broken using water, H and OH. Same way if you break it like this, H and OH. See what are we going to get? RNH2, primary amine, and COOH, that is phthalic acid is what we're getting. So one way of converting this molecule into amine is by carrying out simple hydrolysis. Now I'm taking away this water molecule which I have represented, and up there I'll just mention the product. So this upon hydrolysis, the way I represented it to you, will give you primary amine. So this upon, let's say, acid hydrolysis, giving you what? Primary amine, RNH2. Plus phthalic acid. Another way of subjecting it to hydrolysis to prepare primary amine is by allowing it to react with hydrazine, generally in presence of an alcohol. Generally in presence of an alcohol. Well, just trying to brief you the general mechanism here. Look what is happening. This lone pair will attack at the carbonyl carbon. This bond will break it to make it O minus. O minus will come back because this is a leaving group. So now see what happened. Everyone here. Lone pair of nitrogen attack at the carbon. This bond broke to make it O minus. O minus came back to restored pi bond. So this left bond pair left on the nitrogen. So this N is already having one lone pair. If this bond pair comes, it will become N minus. That N minus will now accept H from either solvent or from this nitrogen atom. Okay, so what are we going to get is, starting with this, here we have C double bond O bonded to, this should be ideally NH2 plus because it is sharing lone pair, but this will undergo deprotonation. So only one H will be left, followed by NH2 carrying a lone pair. And down here, what we have now got is C double bond O, NH carrying R. See, this bond pair came back on N, which made it N minus, which accepted, let's say, H plus from the solvent, let's say from alcoholic OH. So we have got NHR. Now see further, this lone pair of nitrogen of hydrazine is from the other end attacking at the carbon. This bond will break to make it O minus, which will go back to bring back the pi bond, and this will break towards N. So it will become RNH minus, RNH minus. That RNH minus, just like this N minus accepted proton from the solvent, this RNH minus will accept proton from the solvent. Also, this lone pair when attacking at the carbon, it is becoming NH2 plus, so this will undergo deprotonation. So there are two steps taking place simultaneously. One is protonation, other is deprotonation. So protonation from alcohol towards nitrogen and deprotonation here from this nitrogen. So see what we have got. Writing this byproduct. C double bond O, NH, C double bond O, NH, right? NH single bond, NH bonded to C double bond O, and this RNH minus accepted H to give you primary amine. That is nothing but our desired product, primary amine. Along with we are getting thalazine 2,4-dione, thalazine 1,4-dione, not 2,4, 1, 2, 3, 4, 1,4-dione. Well, that is not required to us. What we have understood over here, look here again, we have had thalamide, which we treated with the base. Because this H was protic, we got potassium salt of thalamide, which undergone a nucleophilic substitution reaction here that resulted in N-alkyl thalamide, which either on hydrolysis gives you primary amine and phthalic acid, or it can be subjected to reaction with hydrazine that produces thalazine 1,4-dione along with the desired product, that is primary amine. Now guys, what I want you to understand here, look, the product obtained is primary amine. Let's talk about this. Can we get secondary or tertiary amine? For secondary or tertiary amine to be obtained, this nitrogen should have 2 or 3 alkyl loop. But when you are doing alkylation, we just have got one alkyl present on nitrogen, so there is no possibility of obtaining secondary or tertiary amine. So this method will prefer for the formation of primary amine only. Now let's talk about in primary amine, we have got alkyl amine. Can we get aryl amine? Well, so here the nucleophilic substitution is taking place at the saturated carbon of alkyl halide. Try to recall when we studied aryl halide, we know the fact aryl halide do not readily undergo nucleophilic substitution because of the resonance stabilization that takes place between the halogen atom and the pi bond of the ring. So there is a formation of partial pi bond character, bond length decreases, bond strength increases, hence aryl halide do not undergo nucleophilic substitution unless EWG attached at the second and fourth position. Meaning, just like we cannot get secondary and tertiary amine, we cannot obtain what? Aromatic amine using Gabriel thalamide synthesis. So we know that okay, it has to be primary amine and it has to be alkyl amine only. Now in alkyl also, since it is undergoing nucleophilic substitution, the value of alkyl has to be lesser sterically hindered, such as methyl, primary, or at the most secondary. We cannot get tertiary. Conclusion. Gabriel thalamide synthesis is limited to prepare primary amine. Number 2, in primary amine also it has to be, or it is limited to prepare alkyl amine, not aryl amine. Number 3, even in alkyl amine, the value of alkyl has to be lesser sterically hindered, such as methyl, primary, or at the most secondary. So this 3 important point has to be remembered as far as Gabriel thalamide synthesis is concerned. So guys, so far 2 methods of preparation after introduction of amine that we studied. First one was ammonolysis of alkyl halide, or alkylation of ammonia you can call. Second one, Gabriel thalamide synthesis. Yes. Well, with this now we are proceeding further with something called as amination of carbonyl compounds. So we'll first do amination of carbonyl compound and then we'll carry out reduction of it. Okay, what does this exactly means is, let's say as an example, as a general reaction, we have got some carbonyl compounds, let's say ketone. We are allowing this ketone to react with ammonia, for convenience I'm writing ammonia like this, NH2 minus H plus. Okay, that is ammonia. But I'm writing like this because we have studied carbonyl compound undergoes their characteristic reaction called as nucleophilic addition reactions, right? And generally nucleophilic addition reactions are found to be reversible. So here, let's say NH2 got attached here, this bond broke over O, making it O minus, which accepted H plus. So what we have got here is R, C, R, single bond, OH and NHH. Now this molecule is further heated. This upon heating eliminates water molecule from here, so that the sigma bond will shift back between carbon and nitrogen to give you imine type of compound, nitrogen doubly bonded connected to carbon. So what we have got here, RCR double bond, NH, that is imine, and this imine is further subjected to reduction. So let's say we are carrying out catalytic reduction here, passing H2 gas in presence of a nickel catalyst. So this H2 can be added across carbon nitrogen double bond, so you'll get CH single bond NH2. So the product obtained here is RCHR bonded to NH2, which is nothing but primary amine. Right guys, so what we have done, we first allowed this carbonyl compound to react with ammonia to give you addition product of ammonia, which upon heating undergoes elimination of water to form imine, which upon further reduction with hydrogen gas in presence of catalyst giving us primary amine. The same can also be considered for the formation of secondary amine as well. So just to give you example, let's say now, okay, we have got ketone R, C double bond O R dash, allowing it to react with primary amine, let's say. So R NH2, I am writing it as NHH. So NHH minus NH plus. Okay, so how would we consider here? N attacking at the carbonyl carbon bond would be broken towards O, making it O minus, undergoing protonation, let's say. So we have, look, starting with R, CR dash. Now this has become OH, and up here nitrogen attacked, N, H and R, carrying a lone pair. Fine. So that's the addition product of addition of primary amine to ketone. Now this upon heating eliminates water. So OH and H, this bond will shift back between carbon and nitrogen. So see what we are getting, R, C, R dash, double bond N carrying lone pair and one alkyl group. So this is N-alkyl imine. If this was imine, one of the H is substituted by alkyl, so that is N-alkyl imine. N-alkyl imine is further reduced in presence of a catalyst. So this two H's, if you add across carbon nitrogen double bond, will get CH single bond NHR, that is resulting in the formation of secondary CH NHR. So the product obtained is secondary amine. Right everyone? Now just imagine if you take tertiary amine here. Tertiary amine upon addition will give you some addition product, but it won't have any hydrogen left. So no possibility of formation of imine, hence no further reduction will be required. So tertiary amine won't give you such reaction. But ammonia and primary amine can give you further higher degree or adjacent higher degree amine. Like ammonia gave us primary amine gave us secondary amine. So that is what you call it as reductive amination of the carbonyl compounds, aldehydes and ketones. So guys, 3 methods of preparation of amines we studied so far. The first one was by Hoffman's ammonolysis of alkyl halide or by alkylation of ammonia. We saw in that case we get mixture of primary, secondary, tertiary amine. However, if we intend to prepare primary amine as the major one, we'll have to take ammonia in excess. Second reaction that we studied was preparation of amines using Gabriel thialamide synthesis. And again we saw the limitation of Gabriel thialamide synthesis, like it has to be a primary amine, and then again in primary it cannot be aryl amine. Again, if it is primary, the value of alkyl has to be lesser sterically hindered, like methyl, primary or at the most secondary. And just now we saw a process called as reductive amination. So treating carbonyl compound with ammonia or primary amine, upon heating gives you imine or substituted imine, which upon catalytic hydrogenation gives you corresponding amines. Now once this is done, we study 4 very important, you can say, rearrangement reactions. Well, what we are doing now, out of that the first one is most important and a part of the entire syllabus, be it boards, be it JEE or NET or anything. But we'll be learning 3 more reaction which could be a part of your JEE. So guys, let us understand those 4 simple reaction mechanisms, starting with the first one, Hoffman bromamide degradation. Alright guys, just hold on before we start. Okay, everyone here, Hoffman bromamide degradation reaction. Okay, now you need to look at these 2 words, bromamide degradation. So you'll first have to understand bromamide. It's basically a brominated amide that we'll be taking, undergoing some reaction in presence of base to give you a final product amine, where 1 carbon atom would be lost in comparison to the number of carbon atom in a starting compounds. Hence we'll be calling it as degradation. Okay, so let us see these terminologies one by one. Let's say first we are taking some amide. So we have got RC double bond O NH2. Okay, you can see this hydrogen connected to nitrogen, so it is a protic nitrogen atom. Also, after loss of H+, the conjugate base form can be stabilized by resonance. So this is acidic for sure. So what we are doing is we are allowing this to react with Br2 in presence of base. So since it is in presence of base OH minus, so this base will abstract hydrogen, bond pair will go back on nitrogen. That's how it will make nitrogen electron rich. Okay, so N became electron rich. So we have got R, C double bond O, NH, 2 electron pair and minus. Now this electron rich nitrogen is all set to attack at bromine. So ideally speaking, bromine has 2 identical atoms. So the electron density between 2 bromine should be ideally symmetrically distributed between the 2 atoms. Hence there shouldn't be dipole. However, we know the fact the electron density is never constant. It keeps moving between the 2 nuclei, and hence for some instance there could be development of a dipole instantaneously, which we call it as instantaneous dipole. Or another approach you can say is when such electron rich nitrogen will approach this bromine, since bromine also has 3 lone pair, its electron density will be pushed away. Hence you will be seeing this bromine carrying delta plus other carrying delta minus. So let's say lone pair of N attacked at this bromine and this bond broke over another Br. So we will be getting formation of RC double bond O N H and Br. See what we have got? Effectively, it appears like one hydrogen of amide have been substituted by bromine. Hence, we call this as bromamide. Basically, amide containing bromine or brominated amide is what you can call it as bromamide. So, what we have got here is bromamide. So, this is bromamide. Now this bromamide is further treated with another base. So what we are doing here, we are highlighting this hydrogen atom. Okay guys, so let's say we have H here and that was bromine. Okay, now we are going to treat this with the second equivalent of base which will accept this protic H. So second equivalent of base accepted this H and the sigma bond went back on nitrogen, making it electron rich. So what we are getting here is R C double bond O N carrying C, now two lone pair, which is making it electron rich, right? One was already there, this bond pair came back on N, and there is a bromine present. Now guys, what comes is the important step here. See here, bromine is already a good leaving group. So now what happens is bromine leaves. Now as soon as bromine leaves from here as Br minus, observe this nitrogen. This nitrogen has one bond pair and two electron pair. One bond pair and two electron pair indicate nitrogen will have total only 6 electrons. Having 6 electrons in the valence shell of nitrogen makes this nitrogen electron deficient. Such electron deficient nitrogen species having one bond pair and two electron pair is what we call it as nitrene. What do we call? Nitrene. Yes, I repeat, as soon as bromine leave in the form of Br minus ion, this nitrogen will be left with two electron pair and one bond pair. So such electron deficient nitrogen species having one bond pair and two electron pair is what we call it as nitrene. However, this nitrene is never isolated from the reaction mixture, so you don't get free nitrene available, but you can say for some fraction of second probably it must have been formed. This nitrene is connected to acyl, so we call it as acyl nitrene. Now this step is going to repeat many times in the further reactions as well. So you'll always have an arrangement where there will be one leaving group present at nitrene connected to acyl. So what happens? Look, now these all steps are simultaneous. As soon as bromine leaves, this negative charge delocalizes. So this pi bond breaks towards oxygen, making it O minus. O minus delocalizes back. That pushes the entire alkyl loop along with the bond pair to leave as R minus. That R minus then attack at the deficient nitrogen of what we call it as a nitrene, which is momentarily formed. Look here again, all these things are taking place simultaneously. Br left making nitrogen deficient, lone pair delocalized making carbon pentavalent, so pi bond went back on O, making it O minus delocalized the lone pair back to restore pi bond that pushed away alkyl in the form of R minus. Being nucleophilic, it attacked at the deficient nitrogen atom. So this entire rearrangement that took place, resulted in the formation of, see, R attacked at N. So R bonded to N. One lone pair delocalized to form double bond with carbon, but this lone pair is still intact. I am writing it here. Carbon has restored double bond with O, so double bond O. Fine. This product which is obtained, this is called as isocyanate containing alkyl, so we call it as alkyl isocyanate. Alright everyone, so what has happened? Amide is brominated using base and bromine to give you bromamide. Bromamide further reacted with OH, that is remaining protease also have been removed to give you some species which upon heating, of course this happens upon heating, where bromine leaves, simultaneously some rearrangement taking place to produce alkyl isocyanate. Now you will see in further part of reaction also we are going to get the same alkyl isocyanate. You will see again similarity in remaining three reaction as well, that you will be having an arrangement where there will be acyl nitrene carrying some leaving group present. Okay, as of now we are holding this reaction here. Of course there is no amine is formed yet, so formation of amine will be processed after this, but because in all other reaction as well there is going to be formation of alkyl isocyanate, we will first bring all the four mechanism to the level of alkyl isocyanate, and then one common time we'll see how amine is being formed. Alright guys, this is an important reaction giving you alkyl isocyanate. Now what was the starting compound for Hofmann bromamide? Of course amide, remember amide. Now the next reaction which you call it as Curtius rearrangement, hold on guys, which you call it as Curtius rearrangement. Look at the substrate now. In amide what did we have? We had RCONH2. So the two H's, other than N you had two H's, replace those two H's also with N. You had RCONH2, correct? Those two H's also replaced by N, you will be getting N3. So this is called as azide group, acyl azide. What do you call it as? Acyl azide. I'll write it down. So we have got acyl azide. Well, the same precisely if you have to draw its Lewis structure can be represented like this: R C double bond O N N N. Look at this. This N has 3 bonds, so this is in a neutral state. This N has a 4 bonds, so this is positively charged. This N has only 2 bonds, meaning there has to be 2 more electron pair carrying negative charge. That's the Lewis structure of acyl azide. In this Lewis structure of acyl azide, we can see that this negative charge is alternate to pi bond. So if we draw a resulting structure, negative alternate pi bond, this will go back on N. So we will be getting formation of R C double bond O N carrying 2 electron pair on N. This was already there, new pi bond came, so that made this nitrogen electron rich single bond N triple bond N, and 1 lone pair still intact on the nitrogen atom. This N is still carrying positive charge. Right everyone? See, we have got the same arrangement as in, just let me show you in previous case what happened. You had acyl nitrene, that is nitrogen carrying 1 bond pair, 2 electron pair carrying leaving group bromine. Acyl nitrene carrying leaving group. See what is there now. Acyl nitrene, nitrogen with 1 bond pair, 2 electron pair, and now we have got even better leaving group, rather best leaving group, N2, because it leaves as a stable molecule, and being gas it evolves off immediately. So we have got acyl nitrene carrying the best leaving group. So this upon heating will undergo rearrangement. This upon heating will undergo rearrangement. Well, let's see the rearrangement. If you heat it, this will leave as nitrogen gas. Hold on, I'll show it this way. So now this nitrogen will have 1 bond pair, 2 electron pair. So this is nitrene. This nitrene will undergo rearrangement. How? Exactly the way we showed earlier. Negative charge will delocalize. Make carbon pentavalent. So pi bond will go back on O, making it O minus. O minus will delocalize back to make double bond. R will leave as R minus, which will attack at the deficient nitrogen atom. So, as a result of loss of nitrogen, see what we got. R attacking at N. I'll write down that product here. N delocalize one of its lone pair to form double bond with C, carrying one lone pair on itself. So one lone pair, double bond C, further carrying double bond O. So what is it, everyone? R N C double bond O is nothing but alkyl isocyanate. So we got the same product. Right, see, we had got the same one, alkyl isocyanate. So we had amide in Hoffman bromamide. This two H's you see, both H's we substituted by nitrogen. We got acyl azide, and which upon heating undergone rearrangement to produce alkyl isocyanate. Now see what change we are doing here is, in Hoffman you had NHH. Now I'm replacing this H with OH. If you replace that H with OH, it gives you the starting compound for the Lawson rearrangement. I repeat, how you're going to remember this starting compound is RC double bond O. You had NH2, which I'm writing it as NHH. NHH, instead of H you are taking OH. This is what you call it as hydroxamic acid. So amide was the first starting compound for Hoffman's bromamide. Acyl azide was the second starting compound for Curtius rearrangement, and hydroxamic acid is the starting compound for Lawson rearrangement. So this is hydroxamic acid. Now this hydroxamic acid is further treated with a base. So base will abstract hydrogen, the bond pair will go back on nitrogen to again develop acyl group connected to nitrogen, carrying two lone pair on it and carrying OH. Now several times you will see in several books it is mentioned like we first make this OH into a good leaving group. So let's say if this H is substituted by some benzene sulfonyl group, that is PHSO2, which is also a good leaving group, or if you substitute this by, let's say, acyl group, then this will become carboxylate. So that is going to be a good leaving group. But otherwise in many reactions it is being observed, although there is just OH, because you are going to heat it, even this becomes good leaving group. So see, we have got the same arrangement available now. In case of bromamide, what we had, acyl nitrene carrying Br. In Curtius, what we have had, acyl nitrene part carrying N2. Now instead of N2 we have got OH. So when we'll heat it, this upon heating will again undergo rearrangement. In rearrangement, OH leaves, let's say, as OH minus. Although OH is not that good leaving group, but upon heating it does leaves, or you can simply convert that into good leaving group. And this negatively charged, hold on everyone, there was a negative charge here. Simultaneously what happens, negative charge delocalizes to form pi bond, making carbon pentavalent. Pi bond breaks over O, making it O minus. That will delocalize back to restored pi bond. The whole alkyl leaves as R minus, attacks at the deficient nitrogen atom. So this entire rearrangement produces the same product, R attacked at N. This N has one lone pair intact, other delocalized to form double bond with C, double bond O. So that is again alkyl isocyanate. Alright, so in all these three reactions, Hoffman, Curtius and Lawson, just starting compound changed. In Hoffman we had amide. In Curtius, that CONH2, H2 you replace by again 2 more, and so you got acylazide. And Lawson in NH2, 1 H we replaced by OH to give you hydroxamic acid. And in all cases in general you got formation of acyl group connected to nitrogen carrying some leaving group. Now let us see for the Schmidt reaction as well. It's going to give you the same intermediate alkyl isocyanate which will be subjected for the further reaction. So in Schmidt reaction, what we do, everyone, we allow carboxylic acid to react with hydrozoic acid. Hydrozoic acid is HN3, not ammonia. It's not NH3, it is HN3. Okay, so what we are doing here, look, we have got carboxylic acid. In an acidic condition. Since you treat this with H2SO4, lone pair of oxygen attack at H to protonate it. This OH I'm putting it downward here. And now hydrozoic acid, well, structurally hydrozoic acid you write like this, HN3. Its Lewis structure can be represented like this. This is a neutral N, this is electron rich N. If you draw its precise Lewis structure, you can show it this way. Negative charge alternate pi bond. So we can represent it this way. H and carrying 2 lone pair minus single bond N, triple bond N carrying 1 lone pair. This lone pair I'm putting up. Alright. So if you look at this structure, this structure indicates nitrogen being nucleophilic, can attack at this deficient carbon. So I'm taking that structure here. Okay. Nitrogen, electron rich, carrying hydrogen, further connected to N, triple bond N, carrying positive charge on it. Okay, now look everyone, so this electron rich nitrogen will attack here, this bond will break to give you C single bond OH. So we have got R C single bond OH single bond OH bonded to N electron pair carrying a proton, N only one electron pair because other has formed a covalent bond and carrying one proton here, carrying N2. Right everyone? Now I will see at the same carbon you have got 2 OHs. 2 OHs at the same carbon makes it highly unstable. So this is an unstable species. So what will happen? This will eliminate water. So OH from this carbon and H from this carbon would be lost. So we will be getting, upon heating, first let's show elimination of water being unstable molecule by itself. So remove OH from here and H from here and H. So the sigma bond will shift to give you double bond here. R C double bond O single bond and H lone pair carrying N triple bond N. plus here and lone pair on the other. Alright everyone. Now as soon as this water leaves, it takes away the proton from here. So loss of proton will convert this molecule into RC double bond O. So we got acyl, singly bonded connected to N, carrying 2 electron pair, making it N minus. So that is again nitrene, and carrying the best leaving group, that is N triple bond N, with 1 lone pair and positive charge. Now guys, since we heat carboxylic acid with hydrazoic acid in an acidic condition, now N2 is going to leave. So we'll say this upon heating will undergo rearrangement. So what will happen as a rearrangement? N2 being best leaving group, it will leave, and all of the steps simultaneously. Negative charge will delocalize. Negative charge will delocalize. I bond will break towards O, making it O minus. That will delocalize back to push the entire alkyl as R minus to attack at N. Right everyone? So see, eventually we got the same alkyl isocyanate, R, N, carrying lone pair, double bond C, double bond O. So the product is R, N, double bond C, double bond O, of course with the loss of N2. So guys, what we have to understand in all these cases, in all this reaction, let me show you again. In case of Hoffman, we got alkyl isocyanate using amide. In case of Curtius, we got alkyl isocyanate using acyl-azide. Now the same thing you got in the next also. In Lawson, you got hydroxamic acid converted to alkyl isocyanate. And in Schmidt, you took carboxylic acid in acidic condition with hydrazoic acid. Eventually gave you the same product, this one, which you got in case of Curtius, and upon heating undergoing rearrangement to form alkyl isocyanate. And now let's understand, since in all cases we are getting alkyl isocyanate, what happens the next? So I'm using different color code here. We have got alkyl isocyanate. So I'm writing here further. In all these cases, alkyl isocyanate is treated with water. So we are hydrolyzing it. Look here. Electron rich oxygen attacking at the carbon. This bond will break. Correct? Since oxygen is attacking over here, oxygen will be now becoming trivalent. So it will immediately undergo deprotonation. So let's say proton is lost from here. So effectively what is getting added? OH. So you'll be getting R, lone pair on N, R and double bond C, single bond O carrying OH. So I'll write that. R, N carrying lone pair, double bond C, single bond O minus carrying single bond OH. Right? Now see what happens. This negative charge delocalizes since it is in conjugation with pi bond. Negative charge alternate pi bond. So this will go back on N, making this nitrogen electron rich. So as a resulting structure, we are getting R, N carrying 2 lone pair on it, the negative charge bonded to C, single bond OH, double bond O. Now this will undergo intramolecular proton transfer where electron rich N will accept this, electron rich nitrogen will accept this H, and we will be getting, well, so we'll just mention that this is proton transfer. See, upon proton transfer what we got, RNH single bond C double bond O single bond O minus. RNH one lone pair is still intact, single bond O minus double bond O, and finally this delocalizes, that pushes N in the form of NH minus. So see what is being lost from here, CO2, C double bond or double bond, CO2 is lost and we are getting NH minus. So I'll put it down here itself. We'll be getting RNH minus, RNH minus plus CO2, and this RNH minus will then accept H plus from solvent. So we'll be getting RNH2. This is nothing but primary amine. See, so eventually we got primary amine. So whatever you take, let's say if I'm talking about Hoffman bromamide, in case of Hoffman bromamide as well, we had what? RCONH2, which is eventually being converted to what? RNH2. So if in case of Hoffman bromamide, because that is very commonly used reaction, we are working on this. Let's say in Hoffman bromamide reaction, if I write down the overall reaction, you start with what? Amide. So in general, yes, everyone, what happened here? You started with amide. RC double bond ONH2. We treated that with bromine in presence of KOH. So amide got converted to bromamide. Bromamide in an alkaline condition undergone rearrangement to produce alkyl isocyanate. So we have got RN double bond C double bond O. And just now we saw once this is hydrolyzed, this rearranges to form RNH2. That is primary amine, along with loss of CO2. So in general, if you see the change as such, from an amide, this carbonyl carbon is being lost, you're directly getting an amine. Imagine if there would have been C double bond O, it would have been the same amide. Hence, whenever you see amide has been given, and along with that, if they give you Br2 plus KOH, Br2 plus KOH, which means they're talking about Hoffman bromamide degradation, you can consider that directly one carbon atom would be lost from the starting amide to give you a corresponding amine having one carbon atom lesser. So guys, that was all about Hoffman, Curtius, Lawson and Schmidt reaction. Now just trying to tell you a simple way to remember all of them. Look, well guys, here I'll write it on, do we have a place here? No, we'll write it under the Lawson. Okay, now we know the fact that all these four reactions are, okay, look here everyone, first one is Hoffman's, second is Curtius, Third is Lawson. Fourth is CUET. Okay, now first let's talk about what reactant do we use. In Hofmann's we take amide. So in Curtius, what you'll remember, this both H's will also be replaced by N. So you get acylazide, R C double bond O, N N2, meaning N3 I can write collectively. Yes, we can. So that is acylazide. In Lawson, what we do? In Lawson, we replace one H with OH. So I'm keeping amide as my reference. I'm going to replace one H with OH. So we'll be getting R C double bond O, NH and OH. So that's what we call it as hydroxamic acid. And in CUET, what we do is we get the same compound but by a reaction between carboxylic acid and hydrazoic acid. This is hydroxamic, and what I'm writing is hydrazoic, HN3. By the way, this is not ammonia, this is HN3. Then you can remove water and get the product. Just to remember, you'll be getting similar reactant like this. So guys, these are the reactions and their corresponding some starting compound. Rest you know that every one of this will be converted to acyl nitrene carrying leaving group type of molecule upon heating, which will rearrange to give you alkyl isocyanate, and then you'll hydrolyze it. Well, how I remember this? I told you how I remember the starting compound. But imagine if you remember this, but if you forget which was the first, which was second, which was third, again there is going to be problem, because probably you will not remember, okay, hydroxamic was used for which reaction. So for me, what I remember is, look at the initials, H, C and L. Hydrochloric acid, just a way to remember, this helps me. HClS, so I remember it this way. HCl, we know hydrochloric acid, and just add one in S here. So that's how probably this can help you to remember all the four rearrangement that we studied. Hofmann, Curtius, Lawson and CUET, HCl's. Now once you know this sequence, I have told you how to start with. Hofmann name itself will tell you what is that starting compound. Hofmann bromamide. So start with amide, replace 2H with 2 more N, so acylazide, replace 1H with OH, hydroxamic acid, then take acid and hydrazoic acid, so that you will get corresponding compound. So guys, that was about the four important name reactions. We studied Hofmann, Curtius, Lawson and CUET. Now we'll be talking about preparation of amines from nitriles and oxime, one of the simpler reaction. So from nitrile you can prepare corresponding amines by simple catalytic reduction reactions. So as to put a general reaction, everyone, let's say we have got nitriles. Okay, and imagine if you just pass hydrogen gas in presence of metal catalyst, Rani nickel. So you can see here H2 will be added across carbon nitrogen triple bond to give you CH double bond NH. Add one more H2, so total 2 equivalent of H2 will give you CH2 single bond NH2. That's how this will be converted to R CH2 and NH2, which is what you call it as primary amine. So as an example, let's say we have been given acetonitrile. Acetonitrile is methyl cyanide or ethane nitrile, you can say. Upon passing hydrogen gas in presence of nickel catalyst, hydrogenation across carbon nitrogen bond will result in the formation of primary amine. Okay, the same nitrile can also be reduced using metal acid combination, but in metal acid combination we precisely, when you use sodium metal in presence of an alcohol, we call it as Mendes reaction. So we are reducing nitrile, just the reducing agent we are changing. So as a general reaction, we can remember it this way. Let's say we have got RC triple bond N, which we allow to react with sodium metal in ethanol. Well, for us, we'll just remember this as a piece of information that sodium in ethanol is another reducing agent. So to reduce it completely, as we saw, we need total 4 hydrogen. So I'm writing in the form of nitrile upon reaction with 4 nascent hydrogen obtained from sodium metal and ethanol. So in general, role of metal and acid, we know metal donates electron to any atom, makes that atom electron rich. That rich atom then accepts H. So basically you're carrying out addition of H only. So it's a reduction, but for the representation you can put it this way. Imagine this 4 H's symmetrically added across carbon-nitrogen triple bond. It will result in the formation of RC, 2 H's to the carbon, 2 H's to the nitrogen, resulting in the formation of primary amine. So this reaction where nitriles are reduced to primary amine precisely using sodium in ethanol is what you call it as Mendes reaction. So sodium in ethanol called as Mendes reaction. Now guys, when you talk about reduction of nitriles, similarly amides can also be reduced to corresponding compound. Well, we have studied this way back in alcohol, but just to put it again, suppose if I'm talking about reduction of amides. Let's say we are talking about reduction of amides. So if we take RC double bond O, NH2, treat this with lithium aluminum hydride. We know that lithium aluminum hydride works explosively with water, so we don't take water as a solvent. We rather take ether as a solvent, or you can take tetrahydrofuran as well. Once this is done, then we isolate the intermediate compound and we hydrolyze it further. So a reducing agent, simply considered this way, this carbonyl oxygen will be removed, and instead of that you'll be getting 2 H's, so you'll be getting product R. This is, again, we don't have to really study mechanism in detail. We will just remember this as a reducing agent. So lithium aluminum hydride reduces amide also into primary amine. So far we studied reduction of nitriles. Nitriles meaning cyanide can be reduced by catalytic hydrogenation or by metal acid, that is sodium in ethanol reduction, called as Mendes reaction. And we saw amides can also be reduced to primary amine using LAH, lithium aluminum hydride, in ether followed by hydrolysis. Likewise, third function loop, nitrile, second was amide, third is oximes can also be reduced by the corresponding, hold on guys, for oxime we have no place, okay, we'll write oxime here. So first catalytic hydrogenation of nitrile, second hydrogenation of nitrile using sodium in ethanol, third reduction of amides. Let's talk about oximes as well. So reduction of oximes. Reduction of oximes. Oximes, yes, we have seen oximes. Oximes are the condensation product of carbonyl compound with hydroxylamine. So let's say if we have got oximes of ketone, we write them like this. Okay. Well, so we will allow this to react with sodium metal in ethanol. Sometime you will find sodium metal amalgamated and then ethanol, and you treat this with oxime. So this will be converted to, so let's say 4 nascent hydrogens have been used from this metal acid combination. Add 1 H here, 2 H's here, and 1 over here, and break down the bond. This is just for the sake of remembering, okay everyone? Just a trick. H here, H2 here, and 1 H here. So pi bond have been broken, you'll be getting CH single bond NH2 and H2O. So the product obtained here is R CHR dash single bond NH2. So we've got primary amine plus water. So that's how nitriles, amides and oxime can be reduced to corresponding compounds. And now guys, finally the last substrate, but yes, there are going to be several reactions we'll be studying under this. That is reduction of nitro compound. Again, reduction of nitro compounds mechanism is out of scope for us. It is basically 6 electron reduction of a nitro compound. So let us first see several reactions here. So the first one that we are seeing is reduction using metal acid combination. So when we say metal acid, several combination that we use: tin plus HCl. You can also use Fe plus HCl. You can also use zinc plus HCl. Alright, so any of this combination will be helpful to reduce nitro compounds into primary amines. So let's say as far as reaction is concerned, if we have got RNO2, on arrow, if any of this condition is mentioned, Sn plus HCl or Fe plus HCl or zinc plus HCl. So let's say 6 nascent hydrogens have been produced. Again, metal will have a role of donating electron, making atom electron rich. That rich atom will accept H plus from an acid, and that's how the metal acid combination works. So just for the sake of remembering, nitroalkane upon reduction with any of this 2 oxygen will come out in the form of water. So we'll be writing 2H2 as a byproduct. So see, 2 oxygens have been used and 4 H's have been used. Out of 6, 4 have been used. Remaining 2 H's will combine with N to give you the final product, which is primary amine. Okay guys, so nitroalkane upon reduction with metal acid combination gives you primary amine. The same can also be obtained by a catalytic reduction. So second is by catalytic reduction. Well, so when you talk about catalytic reduction, it is simply, if you find nitroalkane is given, and if you see you're carrying out hydrogenation, if condition is given as hydrogenation using metal catalyst such as palladium, generally palladium is used, you'll see the nitro will be converted to primary amine. So we are getting R NH2 and remaining O are believed to be eliminated in the form of water. So let's write it down as 2H2O. So here we've got a primary amine. These are just going to be piece of informations, and you'll see that several times this question are just asked in the conversion form. Like I've told you earlier, let's say you have been given alkane, you monohalogenated it to give you alkyl halide. That alkyl halide will be further treated with, let's say, AgNO2. So we saw in alkyl halide how AgKNO2 gives you nitrate, but AgNO2 will give you nitroalkane. And then on arrow they'll mention that that is treated with H2PD. H2PD meaning they are saying, of course, palladium, which is charcoal supported. So hydrogen gas gets absorbed on that and reduces this nitro into primary amine. That's how nitro compounds can be converted to amine using metal acid combination or catalytic hydrogenation. Well, there are some cases of selective reduction as well. But prior to that, let's say, now if I'm talking about partial reduction of such kind of nitro compound. So let's say reduction using zinc in ammonium chloride. Now, just for the sake of understanding, I'm simplifying this, guys. Earlier we saw how zinc plus HCl was used to reduce it completely. Now it is not just zinc plus HCl. In addition to that, we are also adding ammonia. Now understand one thing. When we had nitro compounds, let's say, to distinguish, I'm taking aromatic compound. Let's say we have got nitrobenzene. And this nitrobenzene we are treating with two different set of reagents. Either you can take zinc HCl, or let's say the common one which is given generally is tin plus HCl. And now we are taking zinc in ammonium chloride. Okay. So tin plus HCl is a reducing agent. That's a simply 6 electron reduction from the metal. So NO2 will be straight away converted to NH2, which means here we are going to get our desired product, which is NH2. Right, everyone? But now when we have zinc in HCl, look, understand what I'm trying to tell you. Here we have got benzene connected to NO2. If this is completely reduced using 6 nascent hydrogen or 6 electron reduction, we are going to get aniline. Imagine if the same would have been treated with just zinc and HCl, no ammonia. Only zinc and HCl, we would have again got the same product. Now the moment they mention zinc in NH4Cl, meaning other than zinc HCl, we also have ammonia. When we also have ammonia, this ammonia being basic in nature, it is going to neutralize some amount of HCl, which means giving this condition they are trying to tell us, now we don't have excess of HCl produced, we have got limited amount of HCl produced. Now since this HCl is H plus donor, which was reducing this nitro by removal of oxygen, or you can say by addition of hydrogen, because HCl being limited, since it is in presence of base, NO2 will not be completely reduced, it will be partially reduced. Partially reduced meaning the moment you see NH4Cl given, see nitrogen is carrying 1 H, in other cases we are getting 2 H's, meaning instead of replacing entire 2 oxygen, just 1 O is replaced and the other O is still there in the form of OH. So what we are getting is NHOH. So nitrobenzene upon metal acid reduction gives you aniline. Same metal acid combination in presence of base such as ammonia gives you partially reduced product, that is NHOH. Alright everyone. And now other than this, there exists one selective reduction case. I'll write it as D. Again, this is just a piece of information. We'll have to remember this as a data. Reduction using, or rather write down selective reduction. Selective reduction using, well, the reagent that you can have is Either you'll find it is mentioned as H2S, ammonia in ethanol, or you may find, since ammonia and H2S is there, you might find it is written as NH4SH, or you may find it is just mentioned as Na2S. Na2S is very rarely used. Commonly you will find NH4SH is given or H2S ammonia and ethanol is given. Any of this reagent, this combination if given, and if your starting compound is, let's say, metadinitrobenzene, if metadinitrobenzene is given to you, and on arrow, if they mention any of this, let's say NH4SH and heat, or NH4HS they can give you in that way also, or H2S, ammonia in alcohol. Remember, this being selective reducing agent reduces only one of the two. So let's say we are just reducing one of the NO2. So the product will be only one nitro will be reduced to NH2. Well, understanding mechanism of this is out of scope for us, so we are not getting into that. You will see only one nitro have been reduced. So you can say this is metanitroaniline. So metadinitrobenzene have been reduced to metanitroaniline as the product, just as a piece of information in case if they ask any such conversion. So guys, that was all about reduction of nitro compound. We saw nitro compounds can be reduced by metal acid combination or by catalytic hydrogenation, or we also saw we can also use we can carry out partial reduction of nitro compound using zinc in ammonium chloride and selective reduction. So complete reduction, partial reduction and selective reduction case of nitro compounds. Well guys, that was all about methods of preparation of amines. So let me just quickly revise what we have seen so far. Everyone, we started our today's new chapter, that is amines. We saw how amines are obtained as a derivative of ammonia. We studied its structure, we studied the concept of nitrogen inversion, how to find out the optical activity in that case. We then saw the nomenclature of primary, secondary and tertiary amines. Well, once that was done, we entered into methods of preparation. We first studied alkylation of ammonia or Hofmann's ammonolysis, how measured product can be controlled. Second, we saw Gabriel thialamide synthesis. We saw its limitation, how it is used for the preparation of only primary amine, that the value of alkyl has to be smaller and no aryl amines can be obtained. And then we entered into some very important name reaction, Hofmann, Curtius, Lawson and Schmidt. Important one is Hofmann bromamide degradation. Make sure you practice that well. Okay. Well, once that was done, we studied two more methods of preparation of amine. One was from nitriles and the oximes. For nitriles, you can either carry out catalytic reduction or sodium metal in ethanol called as Mendi's reaction. Or we can also prepare it from oxime by sodium metal in ethanol reduction or from the reduction of amide using lithium aluminum hydrides. And then we saw how nitro compounds can be reduced by the complete reduction using metal acid combination, partial reduction, zinc in HCl in presence of ammonia, that is ammonium chloride, and selective reduction using H2S ammonia in ethanol or Na2S or NH4SH. So guys, that is it from our today's class of amines. We are done with our class number 1. In the next lecture when we meet, we'll certainly talk about chemical reactions of amine. Till then, I take your leave. Thank you so much everyone. Not to forget solving DPPs and solving more questions on this. Bye bye everyone. Take care.